Well, welcome back again. Chemistry 3202, course overview review. Unit 2, Section 3, Lesson 3, acid-base stoichiometry. Now this is a continuation of what we were just doing with the titration curve, so you're going to see some similarities here with this. And there's a few new things here, some little twists that we can do with the stoichiometry, and let's just get into it, eh? Here we go. Okay, so calculations involving stoichiometry, page 600, 585, 586. And there's a few questions in your textbook that you can give a try here. And of course, the answers are in your textbook. And these are some of the questions you can throw at your online tutor if you're making use of those as well. Or you can try some of these and throw a question or two in the discussion postings, and we can try and get back to you. Okay, here are the outcomes for this lesson. Only two. Here we go. All right, this is similar to what we just did in the last lesson here on titration calculation. So in this case, we're saying a series of 20 ml samples of sodium hydroxide are titrated. Now, of course, the reason we do so many trials is to try and minimize any error. We try and do it better and better every time, and we're saying that practice makes perfect all the time, right? So if you do 2 or 3 trials, by the time you do the third one, you should be practiced up and you should be a lot better. Okay, so here we go. So in this case, we're taking 20 ml samples, and we've already, in this case, got the average. In the other examples, we had a table. You had to figure out the average. So in this case, we have the average figured out. It's 5.47 milliliters of the 1 molar sodium hydrogen sulfate. So the very first thing we have to do here is we're going to write our balanced equation here for this. And what we're doing, of course, is we're looking at writing sodium hydroxide. And of course, sodium hydroxide is essentially, the sodium is going to be a spectator. So essentially, this is 100% hydroxide. All right. And again, the sodium hydrogen sulfate, essentially, this is, the sodium again is going to be a spectator here. I know some people would have looked at this and said, well, sir, that can't react because you got 2 sodiums. What am I supposed to do with that? But remember, in acid-base reaction chemistry, the sodiums are going to be bystanders. They're not involved in the reaction. So essentially what we have is a reaction of hydroxide with hydrogen sulfate to produce sulfate ions and water. So this is the reaction that we're concerned with right here. All right? We simply write down what we're given and what we need to find. So we're given the volume and concentration of the sodium hydrogen sulfate, which is essentially the same, because this is going to be dissociated 100%. So these numbers would be the same for the hydrogen sulfate. And in the case of the sodium hydroxide, we would have 20 mils of that, which is essentially the same as saying we got a volume of 20 mils hydroxide solution. So there we go. So we do the calculations real simple. For the sodium hydrogen sulfate, we want to find the number of moles, N equals C times E. For sodium hydrogen sulfate, that's these numbers right here. Okay, and then what we do, of course, is in stoichiometry, now that we know the number of moles, got to get your moles, boy. We got our moles, now we do the mole ratio. In this case, it's a 1-to-1 ratio. So we know our number of moles of sodium hydroxide, and then finally, we can calculate the concentration of our sodium hydroxide by saying C equals N over V. Don't forget to change your volume to liters, right? Divide by 1,000 to get liters. And that would be our concentration of sodium hydroxide. So easy enough. Example 2, here's another one. This one's saying Biff and Molly needed standardized hydrochloric acid solution to carry out a titration. It says their teacher provided them with a stock solution. So that's a solution he grabbed off the shelf and said, here, use that. And the stock solution said 1.0 moles per liter, 1.0 molar, which is the same as moles per liter. Now, these guys are not dumb, right? These guys are chemistry students, much like yourself, and they're saying, well, boys, come on, we just can't use that. The teacher just gave us that off the shelf. That's not accurate. We have to figure out what the accurate concentration is. Hence, we have to standardize it. We talked about that in the last lesson. All right? So what we have to do here is we have to standardize it. So what they did was they said, okay, let's go get a standard sodium carbonate sample. They're going to take 1 gram sample of sodium carbonate. And when they did their titrations, they did it, 3 or 4 times. Each time they used a new 1 gram sample. And when they did it, they got an average of 18.97 milliliters of stock hydrochloric acid solution. We want to calculate the molar concentration of the hydrochloric acid. Now you might be thinking, well, don't we already know it? And the answer is no, we don't already know it, because hydrochloric acid, by its very nature, if it's left on the shelf for a long time, can have a variable concentration. So what they're trying to do is figure out the exact concentration. They're trying to standardize it. So here we go. We write our chemical reaction, sodium carbonate and hydrochloric acid. This is going to be a 2-to-1 ratio, because the carbonate ion, of course, is CO3 2-. It's going to take 2 hydrogens to neutralize it. So it's going to be a 2-to-1 ratio here, and we'll take that into account. What we know is we have 1 gram samples of this. We know the volume and concentration of the hydrochloric acid. So the very first thing we got to do here is we got to get our moles. And the only way we can get our moles, of course, is we have to figure it out from the mass of sodium carbonate. So the first thing I have to do is figure out the molar mass of sodium carbonate. That should be easy. 2 sodiums, 1 carbon, and an oxygen. There we go. So the molar mass of sodium carbonate is 105.99. We can now use that when we do our mole calculations. N equals mass over molar mass. So it's 1 gram divided by 105.99. That's the number of moles of sodium carbonate. Now when we look at the mole ratio here, we have to be careful because it's a 1-to-2 ratio. For every one of these, I need twice as much of this. So this is required over given. Required over given. So it's a 2-to-1 ratio. We need twice as much hydrochloric acid. And there we go. That's the number of moles of hydrochloric acid. And then finally we can calculate the concentration. C equals N over V. And again, don't forget to change your concentration, your volume, to liters. All right, divide this by 1,000 to get your liters. Okay, there we go. You can pause this at any time if you want to try the calculations to make sure the numbers are correct. I'm assuming they're correct. Okay, here's another problem. This is a big one. This can show up as a public exam question. This is an excess and limiting reagent problem. Now these guys can be a little bit difficult, but if you're going to follow the method I'm going to show you, then you shouldn't have any problems with these. It's a real simple method. So we're looking for an excess and a limiting reagent. And remember, in a chemical reaction, when we have a limiting and excess reagent, it's the limiting reagent that you do your calculations on, right? That's the one that's going to control how much is going to react and how many products we're going to get and all that stuff. So what we're looking at is the reaction of hydrochloric acid with sodium hydroxide. So that's good. It's a 1-to-1 ratio. We write down what we're given and what we need to find. So we're given the volume of hydrochloric acid, the concentration of hydrochloric acid, the volume of sodium hydroxide, and the concentration of sodium hydroxide. So the question is, the next thing we've got to do is you've got to get your moles. In order to do stoichiometry, you've got to get your moles. So the question is, well, which one do we use? Because we could do N equals CV for both of these to get the number of moles, and that's what we have to do. So the very first thing we're going to do is we're going to say, all right, let's calculate the moles of each one of these. In the case of hydrochloric acid, it's a strong acid, so it's 100% H3O+. So the number of moles of H3O+, N equals C times V, is going to be 0.00210 moles of H3O+. Now you notice I'm not saying hydrochloric acid anymore. I'm saying H3O+. Because hydrochloric acid really doesn't exist as HCl, right? Remember, it's 100% ionized. We do it for sodium hydroxide as well, and again, this is 100% dissociated this time because it's an ionic compound. So really what we're finding is the concentration of OH-, so N equals C times V. So here's our number of moles of sodium hydroxide, or hydroxide. Now what we got to look at is we're saying, hey, this is going to be a 1-to-1 ratio. So we got 0.021 moles of H3O+, we got 0.0029 moles of OH-. We got slightly more of this stuff, don't we? So all of the H3O+ is going to be consumed. Every last one of these guys is going to be neutralized because we got more sodium hydroxide. So the sodium hydroxide solution is going to be the one in excess. And that's what we want to figure out in this case, because this question's saying we want to find the final pH of the mixture. When we mix these two guys together, what's going to be the final pH? So we're saying that hydrochloric acid is going to be all used up, so the hydrochloric acid is limiting, which means the hydroxide is in excess. So every single one of these H3O+'s, because it's a limiting reagent, has now been turned into water. They've been completely neutralized. What we have left floating around in this container is going to be some excess sodium hydroxide. Well, how much sodium hydroxide is left over? Well, we can easily figure that out. The amount of sodium hydroxide that's in excess is equal to the number of moles of hydroxide that we started with minus the number of moles of H3O plus that we neutralized, and thereby we have 0.0081 moles of hydroxide. Now you might say, okay, good enough. Plug that in your calculator, get the pH. No, it doesn't work that way. pH is based on concentration. What we have here is the number of moles. So what we got to do now is figure out the concentration of this new solution. And of course the problem here is that we started out with 28 milliliters of sodium hydroxide, but that number of moles is now distributed throughout the entire volume of this container. So although it came with 28 milliliters, it's actually now been mixed in the entire 48.55 milliliters. So what we're saying then is that if we're going to calculate the new concentration, it has to be based on the total volume. So C equals N over V total, the total volume, and in this case it's 48.55 milliliters converted to liters. All right, and it works out to be a concentration of 0.0167. So now what we have to do is figure out the pH of that. And in order to do the pH, we can do the POH. Hold on now. POH, which is the minus log of OH minus, we get 1.78. And in order to get the pH, remember, we had to subtract for 14. 12.22. It's basic. Now that makes sense. Why wouldn't it make sense? It's basic because we have excess sodium hydroxide. So anytime you do these, you're thinking about this and saying, okay, a pH of 12.22. Yeah, well, we got excess sodium hydroxide. That should make sense. So therefore, we're probably in the right ballpark. Okay, so just to recap of this, you're going to calculate the moles of each. Now you're going to find out which one is in excess, because the one that's in excess is going to determine what the overall pH is afterwards, because that's the one that's going to determine if it's excess hydroxide, it's going to be basic. If it's excess hydronium, then it's going to be acidic. Once we do that, we find out how much it's in excess. Now we find the new concentration by dividing by the total. Lots of times people make the mistake here, instead of using 48.55, the total volume, you guessed it, they would only use the 28.55. So don't forget, this is total volume down here, not just the volume of the sodium hydroxide. Okay, here we go. Here's another one, and in this case they want us to calculate just about everything there is, the pH, POH, hydronium hydroxide, and it's a mixture formed by sulfuric acid and sodium hydroxide. So we're going to go about this pretty much the same way. The only problem being here, of course, is that I'm going to wipe that out over there now for a sec just to get it out of the way. In this case, it's sulfuric acid that's being completely neutralized by the sodium hydroxide. So this is going to add some element of difficulty here, because we have to take into account this 2-to-1 ratio. But we're going to make it easy, because we're going to say, all right, same way as we did it before. Just simply find the total moles of each substance. And in this case, we're saying that, let me just pull it down here. We're saying that, all right, the sulfuric acid is easy enough to find. We're saying N equals C times V, but this is the number of moles of sulfuric acid. When this ionizes, it's going to be a 2-to-1 ratio. So it's going to give me twice as many H3O plus than, say, hydrochloric acid. Hydrochloric acid would only give me 1. Sulfuric acid is going to give me twice as much. So therefore, the number of moles of H3O plus is going to be twice as much as sulfuric acid. There we go. The sodium hydroxide is straightforward. The number of moles of sodium hydroxide, N equals C times V. This is going to give me a 1-to-1 ratio, so this is the number of moles of hydroxide. Now what we have to do is say, okay, which one is in excess? 0.0176, 0.01924. Well, once again, looks like we've got more sodium hydroxide. So sodium hydroxide is the one that's in excess. All right? coincidentally enough, all right, this is the one that's in excess. How much is it in excess? Well, you're simply going to subtract these guys. And there we go. We subtract these guys, and we see that we get 0.00156 moles of OH minus in excess. So we're going to make the prediction now that we should have a basic solution once we mix it all together. All right. When we mix it all together, our total volume is going to be 91.63 plus 40 milliliters. That gives us 131.63 milliliters in total, because now that sodium hydroxide is dispersed in that 131 milliliters and not just the 91. All right, so our calculation here now, C equals N over V total. All right, don't forget to change your volume to liters. And there we go. So it's 0.0115 moles, 0.01185 moles of hydroxide. So now we've figured out the hydroxide, so we should be able to easily get the POH. Okay, and I'll just uncover this here now. POH we can get from this by simply doing the log, 1.93. We can now get pH, because you're going to subtract that from 14. And now that you know pH, you can get H3O plus by doing 10 to the minus pH to get that value. So these are old calculations, but there you go. So again, be wary. These are the two types of problems you could get on the public exam dealing with excess and limiting reagents. And remember, you're trying to figure out which species, the hydroxide or the hydronium, is in excess. That's going to determine whether or not you're acidic or basic after everything is neutralized. Okay, what's left over? So, you know, try some public exam questions. Go look for a couple public exams where this question comes up, and then follow this method, and again, you should have no problems if you calculate the total number of moles of H3O plus and the total number of moles of OH minus. It works well. All right, I'm going to stop there now. Make sure, if you need some help with this, consult your online tutors. Go get some old publics. Don't forget, we have public exams, MLOs, learning outcomes, where teachers are talking about each of these public exams and trying to solve the problems for you. So go check those in the content link of D2L. And see you later.